Well, good evening, class. So today, let's continue with tutorial 11. So first of all, let's take a look at summary. It's about tutorial 11. Now, today, we are going to solve some partial differential equation. All right. So the first method that we are going to do is this direct integration method. All right. So this is the first method that we are going to do. And this kind of method is suitable for PDEs that contain only one differentiation term. Okay, all right. So our PDE can only have one differentiation term. So first, let us look at our tutorial question. Okay, so everyone look at this tutorial 11. There's a question 2, right? So we have this partial differential equation here. So, well, if you notice this equation, the first thing you notice is that how many differentiation terms does it have? All right. So then you see, we only have this u subscript xy, right? And then here equal to 2x e to the power y. So this is the only differentiation term, correct? Yeah. So there's only one differentiation term here. Okay. Yeah. So therefore, for this kind of PDE, it's suitable to use this method, direct integration. Is it okay? All right. So let's go back to this question. Okay, so we decide to use direct integration. Now here, we also have some initial conditions given. So we have u0y given, all right? And we also have ux0 equal to x, all right? So these are initial conditions. And we want to solve for uxy, right? Okay, so let's see how we do it. So we already decided that we'll use this direct integration method, right? Okay, so let's look at our solution here. Right, so we have this partial differential equation here, right? Yeah, so we know that there's only one derivative term here. So the first thing we want to see is we want to see what is the order of this PDE. Right? What is the order of this PDE? Okay, right. So class, what is the order of this PDE? I hope you can still remember what is the order of PDE mean. Order of PDE means what? Is the highest order of derivative of that PDE. All right, so what is the highest order of derivative here? Well, we actually have only one term, right? Yeah, del square u del x del y. So what is the order of this partial derivative? Yeah, anyone or not? What is the order of this partial derivative? Yes, anyone?
Is it first order?
No, not first order, because we got the del square u del x del y. There's a del square u del x del y. So you differentiate respect to x, you differentiate respect to y. All right, so you actually differentiate 2 times. All right, so the order of the PDE here actually is 2. Okay, yeah, so it is 2. Is everybody okay here? All right. Now, why do we want to know about this order of PDE? Well, why do you need to know this order? Well, that's because when we use this direct integration, later on, after integration, we will get arbitrary functions, right? Something like your arbitrary constants, okay? But now it's called arbitrary functions, all right? So how many arbitrary functions will we get? Well, actually it depends on the order of the PDE, all right? It's actually equal to the order of the PDE. Is it okay? All right. So if the order of the PDE here is 2, so that means later on, we expect 2 arbitrary functions. Everybody okay? Right on? Okay, so let's go and do this. Go and do by direct integration method, right? So first of all, let us write out this partial derivative here. Okay, so let me go and write it out. Wow, there's del square u del x del y, right? Now, del square u del x del y. So that means we can del x first, or we can del y first. All right, so it's the same. Whether we differentiate respect to x first or you differentiate respect to y first, it's the same. Okay, so therefore I just choose to write like that. Okay, so I put del u del x and then bracket, then outside I put del y. So when I put something like this, that means that I go and del u del x first, and then after that I go and differentiate respect to y. So that's the meaning. Okay, right. So after you do this, now the first thing you want to do there is to remove what? To remove this del y. All right, so to remove the one outside. Okay, so you want to remove this. Now, how do you want to, how can you remove this? Okay, how you remove this is, I clicked something wrongly. Okay, so I want to remove this del y, right? So what we do is the del y we bring to the other side. Yeah, so you bring to the other side. Okay, so when you bring to the other side, it becomes dy. So that is your dy here. Okay, all right, so when this one bring here, then becomes dy. Yeah, and then here you still have your del u del x. Okay, right. And then after that, you just put your integration sign. Okay, yeah. So this step actually we call it integrate respect to y, right? Because you see here you dy, right? You integrate, right? So that's called integrating respect to y. Okay, right. So then we just go and evaluate these integrals. Now the left side. Now when you del something and then you go and integrate, straight away it will just give you whatever this one is. Okay, straight away it will give you this del something, right? You integrate, right? So it will straight away give you this something here. Okay, and then your this 2x e to the power y dy integrate. So that means only here, when you're integrating, you only consider the y as variable. All right, then what about your 2x there? What about your 2x here? I think I highlight the wrong thing. Okay, so your 2x here, now your 2x here will just be constant. All right, consider as constant. So of course, then you will get 2x, right? Then your e to the power y, you integrate, then of course, you will just get e to the power y. Is it okay? All right, so this one integrate will give you this. Okay, so this is called finish integration already, right? Then after finish integration, what do you do? Now, last time is you finish integration, you go and add a constant, right? Yeah. But now, this one we don't just add a constant, but we are just adding, but we are going to add a arbitrary function. Okay, arbitrary function. Last time is arbitrary constant, but now is arbitrary function. Okay, now this is the arbitrary function fx. All right, this is a function of x. All right, and then of course, maybe you ask me, hey, why is it a function of x there? Well, that's because, when you do this integration here, it's respect to y, right? So meaning that your x here is considered as constant. Okay, so therefore this arbitrary function actually is like arbitrary constant. So it is a function of x. Is it okay? All right, any questions here? Do you all understand why this one function of x or not? Well, that's because in this integral, your x is considered as constant. Okay? All right, so we are now here, right? And then you realize that, now very good, because your del y no more already, right? And now you are left with what? You are left with del x. Okay, so the next step will be, you want to remove this del x. Okay, so what we do is the del x, you bring to the other side and you integrate. Okay, yeah, so you see your del x, when you bring here, then it becomes dx. And then you go and integrate both sides. Okay, so this is what we call integrating respect to x. Okay, now your left hand side, del u, integrate, right? So that one we know already. It will just give us, it will just give us the u. Okay, yeah, it will just give us the u here. And then how about this side there? This side we just go and integrate. So here we integrate respect to x. So meaning what? meaning your e to power y, your y is like constant. All right, so your e to power y like constant. So here you just integrate your 2x. So you all know how to integrate 2x, right? So the x will give us x squared over 2, right? Yep. Okay, so this one will give rise to this. So this term integrate will give us this thing. Okay, then your second term, fx dx integrate. Okay, so that is this term. Okay, finish. Finish already at a constant. Now, this one is not constant, but it is an arbitrary function. Okay, arbitrary function here. And in this integral right above, your y is considered as constant, right? So therefore, our arbitrary function here is a function of y. Is it okay? All right, all. Okay, so actually here we actually got our u already. So our u actually equal to this. All right, and then we see this now fx dx integral, right? So what is that? Well, what is this? Well, you also don't know because our fx is arbitrary function. That means any function of x. All right, so then we just have like that. Okay, of course this one doesn't look so nice. So you want to write it nicer. All right, so then what is it there? So then we reason ourselves that, oh, this fx or function of x, right? You integrate with respect to x, the outcome is also a function of x, correct? Then we just call it by another name. Yeah, so we just call this thing, we just call it hx. Well, that is just another arbitrary function of x. Okay, so this one is our final solution. Yeah, this is our final solution. And if you look at our final solution here, how many arbitrary functions do we have? Class, if you look over here, if you look over here, how many arbitrary functions do we have? Yeah, class, anyone or not?
2.
Yeah, 2. Okay, so your arbitrary functions here will be the h and the y and the g. Okay, the hx and the gy. All right, so 2 arbitrary functions. All right, so well, that is within our expectation. 2 arbitrary functions. Okay, so that is within our expectation. All right, because it is the same as the order of the PDE. Right, so we notice that here this one is 2, this one 2, right? And here also 2. Okay, not? Okay, class. So that completes this question. Any problem? Okay, quite easy, right? So now let's look at another question. Okay, here is another question. This time we have this PDE here. Right, so see our PDE here. This time is a zxy equal to x squared y. Okay, the xy here is in the subscript. All right, so meaning that it's del squared z del x del y. So okay. So well, then the other side is x squared y, right? So if you look at the whole PDE, there's only one derivative term. This is the only derivative term, right? So del squared z del x del y. All right, so then we know already, for PDE that contain only one derivative term, then you want to use direct integration, right? Okay, so that means here we shall use direct integration. So in fact, part A is solve the PDE by direct integration. Okay, then we know that after direct integration, we'll get arbitrary functions, right? So then they give us 2 conditions, right? So you see they give us this condition here, then got another condition here, okay? And this time they ask us to find particular solution. All right, so particular solution here actually doesn't have arbitrary functions. All right, so these 2 conditions will help us to determine the arbitrary functions. Okay or not? All right, so let's go and do part A. So part A will have arbitrary functions. Okay, let's go to the third one. Okay. Oh, I see. Oh, just now I haven't finished the first one, is it? Oh yeah, I forgot the initial conditions. Okay, class, let's finish off this part first. So class, just now, I forgot already. So it's not just asking us to find the general solution. This one actually called general solution. Okay. Well, because they give us two initial conditions, right? So you need to make use of these two. Okay, right. Okay, so we have this thing here. This solution here contains arbitrary function, right? So all solution that contains arbitrary functions, we'll call it general solution, right? So this one is actually a general solution. Well, actually, it's the same as this one here. Okay. Yeah, I just move it to the next page, right? General solution. Okay, now I'm going to use these two initial conditions. Now, the first one is U0y is y, right? U0y is y. So what we do is, inside our general solution, we are going to, go and get this U0y, all right? Now, this U0y, this 0 here, this 0 here means what now? What is 0 there? This 0 here. When they say U0y, right? This 0 means what variable is 0? Yeah, class, anyone or not? Hello, class. When they say U0y, right? So this 0 here means which variable is 0?
X.
Yes, x is 0. Okay, so I'm going to put inside general solution, substitute the x as 0. And of course, the first term will just give you 0. The second term will give you h0. Okay, then your gy, of course, still gy. So here, your u0y equal to this, but this is equal to y. All right, so that is the given one. Okay, now, all right, so from here, straight away, you can find your gy. Yeah, you see, straight away, you can get your gy. Okay, that's good. So what you do is your gy, this gy, right? Now you substitute into your general solution. Okay, so once you substitute in, then you see your gy becomes this y minus h0. Okay, now, well, so at least here, you don't see gy anymore. What remains is h. Okay, well, we have another condition, right? So let's use another condition. Now, another condition is ux0 equal to x. And see this 0 here, right? Ux0. When they say ux0, meaning which variable is 0? Class?
Y.
Yeah, it's y. All right, so I'm going to put y as 0 over here. All right, look at the latest one. So you put inside here. Okay, your y as 0. And of course, your first term will give you x squared. Second term is just like that. And then here y 0, right? And then just minus h0. Okay, and this whole thing is equal to x. Okay, now, all right. Then from here, what can we get? What can we get now? So you realize that here, actually we can get hx minus h0. Yeah, because you see here, what we don't know is hx minus h0, right? Then you see here, you got your hx minus h0, right? So we can just get that one. Okay, so therefore your hx minus h0 is like that. And then finally what? Substitute into here. Yeah, substitute into here. So that's what you have. All right, so we have this thing here. Okay, so when you get this solution here, you realize that, this solution here, there's no more arbitrary function, right? No more arbitrary function. Everything is just x and y, right? Yeah, you don't have unknown functions. So this kind of solution, no more arbitrary function, we'll call it particular solution. Right, so this one, the last line here is called particular solution. Okay, now, all right, all. Any questions?
Sorry, Prof. Can explain how you get gy again?
Gy,
Yes, sorry.
Then here, you use this equation. You use this equation here. Let me change the color here. You use this equation. Then you can get your G1. Can you see? G1.
Yes, thank you.
Yeah, lor. So that's how you get this. Right now. Okay, yeah. Okay, let's do the next question. Yeah, the next question. Okay, so the next question. Well, we already said want to use a direct integration, right? Okay, direct integration. What is the order of this PDE there? Yeah, class. What is the order?
Second order.
Yeah, so it's a second order. So it's 2. So later on, after direct integration, we will expect 2 arbitrary functions. Okay. All right. So let's go and do this. So first of all, let's write down this derivative. Write it down explicitly. Okay. So this time I write del square z, del x, del y. Then just now I already mentioned, right? You want to del x first also can. You want to del y first also can. Right? So here, just for a change, because earlier on we go and del x first, then del y, right? So now for a change, let me go and do opposite. Okay, I del y first, then I del x. Okay, now. Well, I think maybe you all want to ask me, you want to ask if you del x first or del y first, your intermediate answer and your final answer, will it be different? Okay, so my answer is your final answer will be the same, whether you del x first or del y first. All right, but your intermediate solution will be different. Okay, yeah. So intermediate will be different, but the final one will be the same. Okay, now. Okay, so now, so since I write like that, del z, del y, then del x, right? So the first thing I want to remove is this del x. And I mean, now that we have already gone through question 1, right? So you know that this one I'm going to bring here becomes dx, and then I'm going to integrate, right? So that's what we call that's what we call integrating respect to x. See here, integrating respect to x. Okay, so when you integrate respect to x, well, you can expect this up. So here you are left with del and then this thing, right? So when you integrate, you just get this thing. Okay, so that's the left hand side here. And then here you got x squared y dx integrate, right? You integrate respect to x. So that means your x is variable. Okay. So when your x is variable, then y is constant. So here you get x cubed over 3 and then times y. Is it okay? So this one after integration will give you this. Okay, not? So this term, okay? All right. So this is called finished integration already. And then you know, oh, you need to add something, right? Yeah. Add arbitrary function. And then your arbitrary function here is a function of y. Okay, why there? Well, that's because when you integrate respect to x here, your y is like constant. Okay, so when you write fy, actually it's considered as like somewhat like an arbitrary constant. Is it okay? All right, Okay, so our fy is arbitrary function of y. Okay, so now that you are here already, right? So then now you have del z, del y equal to this thing. So the next thing you want to do there is to remove the del y. Okay, so then you know, oh, del y you're going to bring here becomes dy. Then you go and integrate both sides, right? So that thing is, that action is actually called integrating respect to y. Okay, so you go and integrate respect to y. Okay, then this is what you will have. So your del z here, integrate will just give you the z. Okay, then this one, integrate respect to y. So that means your y is variable. Your x cubed there, x cubed like constant. So that's why you see you got your 1/3 x cubed. And then your y, actually you integrate, give you this y squared over 2. Okay? And then your fy, also integrate respect to y, right? Okay, finish. Okay, finish already, then you must add an arbitrary function. And this is an arbitrary function of x. Why? Because when you are integrating with respect to y is the variable. So your gx is somewhat like constant, okay, like arbitrary constant like that, okay? So therefore it's a gx, it's a function of x. All right, okay, y'all. Okay, then come to here. See this blue line or not? Now this fy dy integral. Well, this one doesn't look so nice. So we reason ourselves that, oh, function of y, you integrate with respect to y. All right, so what's the outcome? Well, it's just another function of y. All right, so maybe I can just call it hy. All right, so this is what we have. All right, not okay, y'all. So what we are getting here, well, actually we got our zxy already. All right, so this is our general solution. Okay, and you can see that it contains how many arbitrary functions? 2. All right, same as the order of the equation. Okay, now, so up to here, we already solved part A. All right, so we complete part A already. Now we go and do part B. Okay, part B is you have 2 conditions given. You want to find particular solution. All right, so these 2 conditions will help us to determine the gx and the hy. All right, so let's go and do that. So this one, general solution, I'll bring it to the next page. So this one is a general solution. Okay, so I also write here, this is the general solution. Right. Okay, so now let's go and get part B, particular solution. Okay, I do the first condition first. So zx0 equal to x squared, right? Okay, so someone tell me zx0. What is 0 there? The 0 here means what? What variable is 0?
Y.
Okay, so inside here, this is your general solution, right? Then you just go and substitute your y as 0. Okay, so your first term actually is 0. So your second term is your h0, and your third term is your gx. Okay, so this whole thing is given to be x squared, right? So from here, you can get your gx, right? So this is your gx, so x squared minus h0, right? Yeah. And after getting your gx, you will substitute inside here your general solution. So at least your gx is gone. Okay, so this is your gx here, right? So now this is the latest one. Well, it's still general solution, all right, because it still contains arbitrary function. So now we use the next condition. Z1y equal to cosine y. Okay. This is Z1y. Z1y, right? You see this one here. This one is what variable is 1 there? Yes?
X.
Yes. Yeah, it's x. So I'm going to substitute inside here. We use the latest one, substitute the x as 1. Okay, then it will give you all these things. And this thing is equal to cosine y. Right not? Then after that, from here, I can actually get hy minus h0. Yep, you can actually get this equal to this. And you can see that why I want to get hy minus h0, right? Well, that's because I have it here, right? Then hy minus h0, right? So I can just put in this whole thing. So just put this whole thing in. Right not? So that will give me this particular solution. Right? So this is our particular solution. Yeah. So if we look at this solution here, we see that everything is just x and y. Are there arbitrary functions? No more. All right, no more arbitrary functions. Okay, so this is general solution. This one is particular solution. All right, the first line here got arbitrary functions, right? So call general solution. Then this one, no more arbitrary function. So we call particular solution. All right, okay. So any problem here, number 3?
Hello, Prof.
Mm,
When you say integration with respect to x or with respect to y, the answer is the same, right? That is when the function is continuous.
correct. Your z here is continuous.
If it's not, then it won't be the same.
Yeah, if not, it is not the same.
Okay, and thank you, bro.
Yeah. Prof Teo mentioned that, is it?
Yes, so it's, yeah, he mentioned that, and he said that I think differentiating with the first term first would be a pattern.
Uh-huh. Okay.
Yeah, then if it's continuous, then x, y, and y x is the same.
Hmm. All right. Yeah. Okay, so now, well, I shouldn't show this one first. Let's go to the question now. Let's do number 4 now. Okay. Yeah, number 4. Show that, see this word now, show. Yeah, show that uxt equal to this, f 2x plus 5t plus g 2x minus 5t is the general solution of this PDE. All right, here f and g are arbitrary functions. All right, so here, okay, now that they say f and g are arbitrary functions, right? So now we understand the meaning of this. This means the f is a function, right? And the argument inside is 2x plus 5t. All right, so likewise, now we understand this notation. The g is a function, all right? And the argument name is actually 2x minus 5t. Right? Yep. So there are two things here. Let me change the color. Okay, there are two things here. You want to show that this one is the general solution of this. All right, general solution, actually 2 words, right? So there are actually 2 meanings here. There are 2 meanings. One is general, one is solution. Well, let's talk about solution. All right, what's the meaning? You know, when you say that your UXT is a solution of this PDE, class, when you say that UXT is a solution of this PDE, what does it mean? Any idea?
One of the particular solution.
No. I'm concentrating on the word solution. When you say that something is a solution of an equation, what do you mean?
Answer.
Yeah. It's an answer. All right. So that means this one, that means if you solve this, you will get this kind of a UXT. All right. In other words, solution means that you say that this one is a solution of this equation, meaning that when you substitute this UXT inside your equation, your left hand side must be equal to right hand side. Make sense to you? That is the meaning of solution. Okay, when you say that something is a solution of an equation, right? What do you mean? Well, the meaning is if you substitute that thing into the equation, your left hand side should be equal to right hand side. All right, so in other words, to phrase it differently is this UXT must satisfy the equation. All right, must satisfy the equation, meaning that you substitute inside all, your left hand side must be equal to right hand side. Everybody clear? I hope you are clear. So that's the meaning of solution. Okay, then let's look at another meaning. General solution. Now, general solution means what? Well, general solution, just now you all know already what? General solution contains arbitrary functions. All right. General solution contains arbitrary functions. So that makes it special, because it has arbitrary functions. All right. So that's the meaning. Okay, now, yeah. So actually here the emphasis is on the general. All right. So meaning that this expression contains arbitrary functions. Okay, right. So here, if you take a look at this thing that they say you want to show as a general solution, right? So if you look at your this uxt here, right? If you look at your this uxt here, right? How many arbitrary functions does it have there? Can you tell me? You know, your uxt equal to this plus this, right? How many arbitrary functions does it contain? Hey, class.
2.
Yes. So this one has 2 arbitrary functions. Right. So maybe I type here. So this one got two arbitrary functions. All right. There are 2 arbitrary functions here. Okay. Now, if you look at the order of the PDE here, what is this order?
Second.
Yes. So the order of PDE here is 2. All right, because the highest order of derivative, this one is a del square u del t square. This one del square u del x square. All right. So the highest order of derivative is 2. Okay, so order of PDE is 2. So therefore, your this thing got 2 arbitrary functions, right? Then, which is the same as the order of the PDE, right? This one also 2, right? So from here, you can say that if you can show that your uxt is a solution of this PDE, then it must be the general solution. All right, because we have the knowledge that general solution of this must contain two arbitrary function. All right, then this guy contain 2 arbitrary function, right? So if it is a solution of this equation, then it must be the general solution. All right. Well, I hope you get the argument. Any questions or not? Okay. Well, if no question, so that boils down to what? That you need to show that your this uxt is a solution. All right. So that boils down to you need to show that it is a solution now, because the general solution will automatically follow. All right. So actually what matters here is you need to show that it is a solution. Once you show that it is a solution, then due to the fact that it has 2 arbitrary functions and the order of the PDE is also 2, right? Then you can conclude that this is the general solution. All right, so I hope you get it all. Okay, now I come to the next question now. How do you show that, you say show, how do you show that this thing is a solution of this PDE there? How to show that uxt is a solution? How do you show that uxt is a solution?
Differentiate left and right side and show that left and right is same.
Yeah, yes. So what you can do is that you go and substitute your u into the PDE, okay? The PDE, and show that what? Show that your left-hand side is equal to your right-hand side. Okay, so this is our plan. All right, so how do you show that uxt is a solution? Do we have to go and solve this? You need to go and solve this or not? No, you just go and substitute u inside. Okay, put into the left side, put into the right side, and show that your left-hand side equal to right-hand side. Okay, all right, all. Okay, so now this is our plan now, and we are going to do this. We are going to substitute u into the PDE. Okay, so now let's look at the solution. Yep. Now our this uxt, the one you want to show is a solution, right? It's a function of 2x plus 5t and also a function of 2x minus 5t, right? So this 2x plus 5t, this 2x minus 5t, is going to be troublesome because it's not simply x and t, but you can see that it involves both x and t, right? So what we do here is we'll call it by a different name. So I'll call w as a 2x plus 5t, and then I call this b here 2x minus 5t. All right, so that this this thing that you want to show is a solution now will become like this. It's okay. So from here, all right, now we can just write U equal to FW plus GB, and we'll work from here. All right, because here it is simpler, because now it's only like a function of W, right? And here is like a function of V only, right? Yeah, so it's somewhat like single variable. Okay, so that's what we want to do. And before we carry on, later on, I will need all these partial derivatives. All right, so these are del W, del X, del W, del T, del V, del X, del V, del T. So I need this later on. Okay, class. Let's see. Del W, del X, partial derivative with respect to X. What will that be? Your W is 2X plus 5T. If you differentiate with respect to X, what does it give you?
2.
Right, so you get the 2 off. So del W, del T there, quick.
5.
Okay, then del V, del X there, this is 2X minus 5T.
2.
And then this one?
Minus 5.
Yeah. All right, so I hope everybody is okay with this. So this one, okay, y'all. Okay, so I'm going to proceed to substitute this U. This one here. I'm going to proceed to substitute it into your PDE. All right. Then if you take a look at your PDE, what do you have? Oh, I got a UXX. Now I see that there's a UXX, right? So that means I need to find del square U del T square. I can also see there's a UTT. All right, so I need to find del square U del T square and del square U del X square. Okay, so this thing I'm going to differentiate respect to T 2 times, also respect to X 2 times. Right? Yep. So this is the thing that we have. Okay. So first of all, I want to get UTT. So what we do is you go and differentiate with X with respect to T 1 time first. All right, so we do step by step. We cannot straight away differentiate 2 times. So we do 1 time first. Yeah, so del U del T, here del F del T, here del G del T. Yeah, so I think this one no problem, right? Okay, then the next thing is, let's look at this term here. Del F del T. Del F del T, right? But you realize that your F is a function of omega. You see, your F is a function of omega. But you are differentiating respect to T, a different variable. This one is a function of omega. Just now I call it W, look, a function of W. And then now you want to differentiate respect to T. All right. So similarly, this one del G del T, right? Del G del T. But this G is a function of V. It's not a function of T. Okay. So how do you handle the differentiation? Any idea or not, class?
Put a prime.
Put a prime. You put a prime also same thing. Well, even if you call this F prime, then I mean it's a derivative respect to T, then you just change the representation only. But you don't solve this fact that it's a function of W, but you're differentiating respect to T. How can you do that?
You F prime the W, then differentiate the W with respect to T.
Actually, what you're saying is called chain rule. No chain rule or not? This one is called chain rule. All right. Yep, it's called chain rule. So your first term del F del T, you call it del F del W, del W del T. All right. So this one actually equal to this thing. Okay. So likewise, your del G del T, because your G is a function of V, right? So you can del G del V, and then after that times del V del T. Okay, so it's like this. Is this okay, class? This thing, del F del T equal to this, actually is called chain rule. All right. It's very easy to see this. In fact, I mean, you can imagine, you know, here del F del W, del W del T, right? Now, of course, this one you cannot do, but what I mean is you just imagine only. You see, it's like in your mind, these two like, wow, like cancel away, right? Then cancel away, you see, give you back your del F del T. Right? Similarly here, you see, in your mind, these two can cancel away like that, right? Then it will give you your del G del T. Is it okay? Yep. Class, okay or not? Okay, right? Yep. But of course, you cannot cancel. But what I mean is that if you view it this way, then you can really see that this one is equal to this. Okay, so now we carry on from here. Now you see this del F del W, right? Del G del V, right? Do we know them? Yeah, we know them. Then you see your del W del T here. Then your del V del T also here, right? So you actually know them. So you put in the numbers. Yep, put in the numbers 5 and minus 5, right? Yep. And then here, my del F del W, I call it F prime W. This one there, I call it G prime V. Then this one is a simplification. Okay. So class, any problem until here? It's okay, right? Yeah. So this one okay. Then now I'm going to differentiate with respect to T once more. Yeah, because this is my aim, right? I want to get UTT. That's del square U del T square. So now I have 5 del F prime del T del G prime del T. All right. And then the same problem again. What I mean is that the same problem, meaning that your F prime is a function of W, but you are differentiating respect to T. Okay, so similarly, your G prime is a function of V, right? But you are differentiating respect to T. So we'll apply our chain rule again. So chain rule once more. This is your chain rule. Del F prime del W, del W del T. And this one is del G prime del V del T. Okay. Del F prime del W. I can call it what now? Call it F double prime. F double prime W. And this one called G double prime V. And then this del W del T del V del T. You know the numbers already, right? Just go and put in. So class, any questions until here? It's all right? All right, all? Okay, so I got my UTT already. And of course, the next thing to do is UXX. Yeah, the next thing to get is actually UXX. So the next one is I want to get XX. Right, so that means del square U del X square. And then we'll find that it will be very similar to what we have here. Okay, instead of del U del T, now you will have what? You will have del U del X. So this one will change to X, right? Then of course this will change to X. This will change to X. Okay, your chain rule will still happen, but now it's del F del W del W del X del G del V del V del X. Can you all see? You just change the del T to del X only. All right. So if you do that, and then when you come to del square U del X square, also the same thing. Then you will get the answer. Okay. Of course, the answer will be different because here you will have del W del X del V del X. The numbers are different. All right. But the way of doing is the same. All right. Okay. So you just change your del T to del X. All right. So if you do this, so that's what we call similarly. Similarly, that means your del T, earlier on you got your del T, right? Then you just shift to your, change it to your del X. Okay, yeah, so you just do that. Is that all right? So then you'll be able to get these two. Okay, not? Yeah. Yeah. So everybody okay now? Yeah. So this one you need to go home and write down your details. Okay, so now I got UTT, I also got UXX. So we are ready to put in the left-hand side and the right-hand side of the equation. So let me put in the left-hand side. Left-hand side is 4 UTT. All right, so you put in your UTT, simplify. Then your right-hand side there is 25 UXX. You put in your UXX, you also simplify. All right, so obviously, we can see that this one and this one are the same, right? They are the same, right? Yeah, so meaning what? Meaning that your 4 UTT equal to 25 UXX. All right, so that means you get what? You get the PDE, your left-hand side equal to right-hand side. So left-hand side equal to right-hand side, right? So therefore, this U is the solution. All right, so left-hand side equal to right-hand side tells you that this U is a solution of the PDE. All right, and then just now I already explained to you, once you can show that it is a solution, that means it is the general solution. All right, why? Because it has 2 arbitrary functions. And then your PDE, the order is also 2. So coincide, right? So therefore, this solution is the general solution. Okay, yeah, class, any questions? It's all right? Okay. Okay, class, let's do another question here. So now we are into tutorial 12, Yeah. So you want to show that the solution obtained by this method of separation of variables. So you see, wow, we got a new method here. Just now what we did is direct integration, right? But now it is what? Method of separation of variables. So you want to use this method and show that this is the PDE, right? Show that the solution is like this. Yeah, I want to show that the solution is like that, where K and lambda are constants. Okay. Right. So first of all, let's look at our PDE. This is our PDE, right? Now, UX subscript X, that means del U del X, right? And then T times UT. UT means del U del T, right? So this PDE here has how many derivative terms? Yes, how many derivative terms there?
2.
Yeah, there are actually 2 terms here. You got a del U del X, you also got a del U del T. All right, so if we look at our summary, can we use direct integration? This one like not suitable because this one is only for PDE containing 1 differentiation term. But just now our question got 2, right? So this one not suitable. So now we are not doing direct integration. Okay, so we are going to introduce this method. It's called separation of variables. Now this separation of variables is also not safe for all kinds. It's also for specific types of PDE. All right. So you see, it's for a linear PDE. Not only linear, must also homogeneous, and must have a homogeneous boundary conditions. Okay, linear. Linear. You remember last week we talked about what? We talked about only U, right? So only U means linear. Okay. And homogeneous, homogeneous, we also talked about it last week, right? So let's see this question is it linear and homogeneous? Not this question. Question is here. This thing, is it linear? Is it linear? Is it only U? Only U or not? This one. Y'all remember last week we say the bread talk, right? The yam paste bun is called only U, right? Yeah. So this PDE, is it only U?
Yes.
It is only U. All right. The left-hand side only U. The right-hand side also only U. This T is just a independent variable, so it's not U, right? So you multiply to U is perfectly okay. All right. So this one is linear. All right. And you can also see that it is homogeneous. It is also homogeneous. Why? Because there's no term without u, right? Every term got u. There's no term without u. So therefore, it is a homogeneous equation. All right, so therefore, it's suitable to use this method of separation of variable. Okay, so now we know or want to use this method, right? So let's go and talk about this method. What is this method about? So now we are here. Okay, separation of variables method. Now here, what we do is we assume that the solution is of this form, function of x times function of t. All right, this is our assumption. Yeah. So I mean, from here, you also understand why we call it separation of variable. Because here you're assuming that your solution can be separated, the variables can be separated, into a function of x and a function of t. Okay, so it's separable, right? Separation of variables. Okay, so after this, so you assume that the solution is like that, right? Then after this, what do you do there? After this, then we got several steps. Hey, let's look at step 1. So first of all, you assume that the solution is like that. Okay. Then after this, then you go and substitute into your solution. Substitute into your PDE. Okay, because you say this one is solution. So you substitute into your PDE. That will give rise to 2 ordinary differential equations. Okay, one in x and one in t. Okay, so anyway, you go and substitute into the PDE, and then from one equation there, it will give you 2 ordinary differential equations. Okay, then the step 2 there is you go and solve the ODE in x. This ODE in x, you go and solve first. Okay, so then it will give you a solution of fx. Okay. Then the third step there actually is go and solve another ODE. This time is to go and solve the ODE in t. All right, so this time is you go and look at the ODE in t. Okay, yeah. So this one is you go and solve ODE in x, right? Then step 3 is you go and solve ODE in t. All right, and that will give you this GT. Right, so that means you find your fx here, and find your gt here, and then you can just multiply them together. So that's how you get your solution. All right, yeah. So this is what we do. Okay, now, yeah. Okay, so let's go and illustrate this technique. Yeah, so let's look at our solution. Okay, so the first step is what? First step is you assume that the solution is uxt equal to fx times gt, right? Okay, so you see, to solve this, let a solution be this. All right, you realize that I use this word let. See this word let or not? Let all means it's like assume. You assume that the solution is like this. Okay, a function of x times a function of t. Then the next thing is I'm going to substitute into the PDE. Now, since you say this one is a solution, right? Why you say it's a solution, so that means you put into the PDE here. Then your left side must be equal to your right side. Okay. Now, when you want to put in, I notice that here I need ux. I need a del u del x. Okay. So from here I go and compute my del u del x. All right. So differentiate respect to x. Now, because this is just fx times gt, right? So this is simply f prime x gt. Is it okay? And of course, my f prime x here, my f prime x actually got what meaning there? Actually has the meaning of df dx. Actually has this meaning here. Is it okay? Okay, then the next thing is I also need the ut because in the PDE it also has ut, right? So that means I also must compute, in fact here I together with the t also, this is actually tut, okay? So your del u del t, that's my highlighter. Okay, so my del u del t, okay, your u is here, right? If you go and differentiate, respect to t, you are going to get this. It's okay, fx g prime t. Yep. Now, of course, what's the meaning of g prime t here? G prime t, it has the meaning of dg dt. It's okay, class? So like this, all right, not? So now know how to get from here the del u del x and the del u del t. Yeah. Okay. Yeah. Okay. Then the next thing is, now since you say that your u is a solution, right? Solution means what? When you put into your equation, into your PDE, the left hand side must be equal to right hand side. This is actually the left hand side. This one actually is the right hand side, right? So it is a solution, right? So left hand side must be equal to right hand side. So you put this one equal to this one. So that's how you get to here. Here. Then the next step is, now you got your equation here. What you're going to do now is all the t term one side, all the x term one side. When you separate the t term one side, the x term one side. So let's see how we separate. Or you can just divide here, divide there, and separate them. So in fact, you see that my fx here, I don't want to highlight so many things. My this fx here, okay. My this fx here, I go and divide here, right? You see, my fx divide here, and then my this gt, I go and divide to another side. So that's why I have it here. Okay, not? Yeah. So this is what we have. So we'll have this one equal to this one. Okay, and then we put this. We say this is equal to lambda. Yeah. We say this one is equal to lambda, where your lambda is a constant. Right? So this one is actually I put in myself one. Initially, I need get this one equal to this. Right? And then I say that this is equal to lambda. Right? Lambda is a constant. Now, what's the reasoning behind? Why I can say that, this one equal to this one equal to lambda? Why can you say that it is equal to a lambda, equal to a constant? Well, the reason is that because this thing, this one, this whole thing, f prime x over fx, right, is a function of x. Yep. And then this whole thing, t times g prime t over gt, right, is a function of t. Okay, so you think about it yourself. Function of x equal to function of t, right? X and t are two different independent variables, right? So how can function of x equal to function of t? So you think, how can it be possible? All right, unless both are equal to a constant. All right, so that means actually they not depend on x, also not depend on t. Actually, both are equal to a constant. Is it okay? All right, so that's the reasoning behind. All right, so I shall call this equation star. Now, this equation star here is going to give me two ordinary differential equation. Right, that's our actually the step one here say will lead to two ODE, right? So if you put here, I think change the color, Okay, yeah, before I change the color, maybe remove all this. Okay, right. So if you put this one equal to lambda, all right, f prime x over fx equal to lambda, right? So this will give you a ODE in x. Is that right? You cross multiply, it will give you ODE in x. And then, wait, let me change color. If you go and do here now, you take this one equal to lambda. Okay, this one function of t here equal to lambda. Then you also go and cross multiply, right? So that will give you a ODE in t. Can you see? All right, so the green one will give you a ODE in x. And then this beige color one will give you a ODE in t. So that is the meaning. That is how we can get two ODE. All right, one in x and one in t. Can you all see? All right, so this is actually the first step. All right, so I actually go and get the ODE lah. Okay, go and get the ODE. Okay, so I'm getting the ODE here. All right, I'm just showing you here just now the meaning of f prime x, right? Which I've written earlier. Yeah, I clicked the wrong thing. Okay, so this is my f prime x, right? There's a df dx here, right? And I put f prime x over fx equal to lambda. All right, so this is the one. Yeah. So this will give me a ODE in x. All right, so itself here is already a ODE. So now the next thing is I'm going to solve this. So actually I go to step 2. I want to solve this ODE in x. Okay, now how to solve this? Now f prime is what? Df dx. So let me put that in. So your f prime is your f prime, right? Is your df dx. So I got my 1 over f outside. Okay, equal to lambda. All right, everybody here okay? Yeah, from here, how to get to here? Well, it's because f prime is df dx. Okay, now I look at this. Now very easy. I can see that everything can be separated. So df and f I put here, then the dx I bring to the other side. Okay, and I bring to the other side, and then I integrate both sides. Is it okay? All right, so this here we separate the variable. Okay, then go and integrate. Okay, df over f integrate. What does that give us there? Wow, it actually gives us this ln f. Your left hand side here actually is the ln f. Okay, then your this lambda dx integrate there. Lambda is a constant. So basically it's dx integrate. So that will give you your x. Okay, finish. Plus constant. Is it okay? All right, Okay, now I think one more step to get the f. So our aim is to get the f. So ln f equal to this. So from the definition of ln, what does it mean? It means e to a power of lambda x plus c is actually equal to f. Okay, that's the meaning of the ln, right? Yeah. So fx is equal to this. Okay. And then here, c is arbitrary constant, so I get e to the power of c, right? Maybe I can call it another name. I see here I separate like that, right? So your e to the power of c, actually I call it k1. So here, highlighter, this e to the power of c, actually I call it k1. Okay, no? Yeah, so that's what it is. Any questions here, class? All right, now. This one here, anyway, this one here is equal to this one. I hope you all know this formula. It's actually a very famous formula, right? Dx over x, you integrate this one. Everybody know this formula? This is our ln x. This is our ln x, right? Yeah. Okay. Yeah. Any questions here, class?
Ma'am, can you explain again how to get the 1 over f in the third line?
You mean here?
Yes, ma'am.
That's by using this. Your f prime is df dx. So you put your f prime in, so that's your df dx, right? Then this over f is the 1 over f here.
Okay, thank you, ma'am.
All right, all. Okay, now I'm going to step 3 lah. So now I'm going to look at the ODE in T. All right, so remember how to get the ODE in T? We look at the beige color line, right? So T G prime over G equal to lambda. Okay, so we get from there. And here we also write down the G prime T means dg dt. Okay, so this is how I'm going to get it, right? So I get G prime over G is lambda over T. This one is actually just from here, from this Page equation. G prime over G, the T you divide over, so equal to lambda over T. All right, so that's this one here. Okay, now the G prime, I'm going to put dg dt inside. So this one becomes like that. So this one you all know, right? So that's because my G prime is dg dt. Okay. Then I find that, I can separate the variables, all the G one side, all the T and R side. Then I'll be able to integrate that. Yep. So this is what I have. Okay. Now I'm going to integrate all. dg over G integrate. That's our famous formula, right? That's ln G. Then here, lambda constant. How do you integrate 1 over T dt? Actually, it's the same formula, right? Just ln T. Okay, finish. Class C. Okay, my aim is to get the G. So G is e to the power of this thing, right? Yeah, e to the power of that thing. Now we must remember our ln. Yeah, this one ln T, there's a lambda outside, right? How about I bring the lambda inside the ln? I can do that, right? If I bring inside all, becomes T to the power lambda. Okay, and here we got e to the power C. C is a constant. E to the power C is just another constant, right? So this one, I can just call it K2. Yeah, so this is my K2. All right, and also e to the power ln this actually is just this thing. Okay. This one I hope you all know also. E to the power of ln x is equal to x. Yeah, equal to x. Right? Yeah, this one is equal. So you all know this? Well, if you don't know, now you know that. E to the power ln whatever is just that thing. Okay, class. All right now. Okay, so you see, your second step, you get your F already. Then your third step there, you go and get your GT, right? So now what? Then now you just multiply together, because you assume this one is a solution. So Fx times GT, right? So you put in your Fx, you put in your GT. Then K1, K2, they are all constants. So how about you combine them and call K? Then K is also a constant, right? Then here you get e to the power lambda x, T to the power lambda. Okay, so we have shown that your solution is of this form. Okay. Yeah, class, any problem? Class, okay or not? Any questions? Okay, so this one okay, y'all. Okay, let's do the next one. Right. Okay, now this question here. We want to solve this equation. This is our PDE, y'all. Our PDE, ut equal to 2uxx. All right. Okay, so look at this. Class, can you tell me how many differentiation terms do we have here? And look at this PDE. How many different?
Two.
Two. There's a ut, there's a uxx. So there are two differentiation terms. All right. So if we look at our method, just now on the first page, right? Can we use direct integration? Cannot, because this one is only for PDE containing one differentiation term. But now we got two, right? So therefore here we are trying this separation of variables method. Okay. Now this is for linear homogeneous PDE with homogeneous boundary condition. Just now our that problem doesn't have boundary condition, so this one doesn't apply. Okay. Homogeneous boundary conditions means zero boundary conditions. Let me type here. zero boundary conditions. All right, so that's the meaning of homogeneous boundary conditions. Okay, so let's go and see this question. Is it like that? Hey, this one, this thing. Look at this highlighted PDE here. Is it linear leh? Is it linear? Linear or not? Is it only U? Is it only U? Only U means linear. Only U?
Yes.
Only U or not? Only U. Okay, because the left side only U ma. Then right side also only U, right? So this is linear. Is it homogeneous? Yes. Yes, it is homogeneous because there's you don't have a term just involving x and t, right? Yeah. So when you bring all the U terms to one side, you're going to get 0 lah. All right, so it's homogeneous. Now, here we have a homogeneous boundary conditions. This is a homogeneous boundary conditions. All right, why? Well, because you can see that it's all equal to 0, right? U0t equal to 0, U3t equal to 0. These are boundary conditions. All right, why I call boundary then? Because they are conditions at the boundary of x. This is when x is 0. This is when x is 3. Look here. Your x is between 0 and 3. All right, so the boundary of x is 0, 3. So therefore, these two are called boundary conditions. All right, and then because it's equal to 0, here also equal to 0, right? So they are called homogeneous boundary conditions. Okay, now, all right, so it fits. So therefore, we can use a separation of variables method. Okay, right. And then we are also given this ux0 equal to this thing. Now this one, ux0. ux0 means t is 0, right? T is 0. So t is 0 means initial condition, right? So this one is called initial condition, right? Okay, just this one is this, okay, homogeneous boundary condition, and this one is initial condition. Okay, right. Yeah. And of course, the third one here is just saying that the absolute value of uxt is less than m. So meaning that u is bounded. Okay. Yeah. So part A is we want to convert this PDE problem into a separation of variable formulation. And we want to find the corresponding boundary and initial conditions. Okay. Then part B there is you want to solve for uxt. Yep. So let's see how we do this. Okay. All right. So we want to do separation of variables method. Yeah, separation of variable, right? So separation of variable, what does that mean? The first thing is you let a solution. Okay, you let a solution be uxt equal to function of x times function of t. Okay, so that means you are able to separate the variables x and t. So that's the first thing. You let means assume. Assume that the solution is like that. All right. Now, since this one is a solution, right? So if you substitute into the PDE, it should be equal, right? Left hand side equal to right hand side. Okay, so I want to substitute into the PDE. Okay, ut. I need to find ut. Ut. Here actually I straight away substitute lah. So you differentiate respect to t. That will give me differentiate respect to t. Then of course you just get fx g prime t. Right? Yeah. Now the right side is 2 times uxx. See the 2 here, right? Okay, now uxx. Differentiate respect to x 2 times. So that will be your f double prime x gt. Is it okay? All right, of course here, you know the meaning of f double prime, right? F double prime x. So meaning what? Meaning that d2f dx square. Okay, d2. Well, I cannot type 2. d2. So this is a superscript. So it's a d2f dx squared, right, over this one is over dx squared. So dx squared. Okay, all right. So this is the meaning of f double prime x. All right, so now so it's equal already, right? So what we need to do now is all the x term one side, all the t term another side. Yeah, so just put all the x term one side, all the t term another side. And x term equal to t term if both are equal to a constant. All right, so therefore you see here equal to mu. Mu is a constant. All right, okay now. Okay, and then you know that from here I'm going to get 2 ODE. Okay, how do I get the ODE? Now this one equal to mu. All right, then you go and cross multiply. That will give you this. Okay now. And then another one is another one, right? Yeah. Now another one will be this. You put this one equal to mu. Also go and cross multiply. That will give you this. Is it okay? So from here I'm getting 2 ODE. Yeah. So let's look at our summary. So actually here, right? So the step 1 here, I will get 2 ODE, right? So 1 in x, 1 in t. Okay. So of course now I want to go to step 2. Now step 2, I actually want to go and solve the one involving fx first. That means I want to solve equation 1 first. Okay. So let's go and solve equation 1. Of course, before we do that now, this mu here, this constant here, well, actually got a lot of theory inside. Okay, now this constant, it can be positive, can be negative, can be 0. Okay, and inside our lecture notes, we actually went through the 3 cases when mu is lambda square, meaning that mu positive. And also when mu is minus lambda square, meaning mu negative, right? And also when mu is 0. So there are 3 cases. So inside our lecture notes, we actually went through all these 3 cases. And we realized that some of the cases actually are not valid. When you say not valid, I mean what? Meaning that, well, maybe if those cases, maybe they cannot satisfy, your boundary conditions. If it satisfy, maybe cannot satisfy for real values of lambda. Okay, so that's one thing. Or maybe it will give us trivial solution. So normally this will be the cases. So that make it not a practical case. All right. So we don't want mu equal to lambda square. We don't want lambda to be a complex number, right? Yeah. So that's one thing. And another thing is well, sometimes you solve, maybe you just get your uxt equal to 0. Okay. That's called trivial solution. So that one we also don't want. Okay, so we actually, we put here see lecture notes, right? So we realize that in this kind of situation, only mu is negative. It will give us a meaningful solution. All right, so therefore we say let mu be minus lambda square. Okay, so actually here, inside here, actually we've gone through the 3 cases. So we put here see lecture notes. Right? Okay, so we let mu be minus lambda square. And we know that by doing so, we'll get a meaningful solution. Okay, it's not something trivial. All right? So if you put mu as minus lambda square, you put into equation 1, you want to solve equation 1 first, then your equation 1 will become like that. Okay, so instead of minus mu there, it becomes a lambda square. Right, so now this one is like ODE, right? So do we know how to solve this there? Well, actually we know. I mean, maybe from year 1. So this one is actually like that. All right, for you is last semester, your maths A. So from here, from this equation, we know that the solution is like this. Okay, so here there are actually three constants. A is a constant, B is a constant, and of course lambda is also a constant. All right, so actually there are three unknown constants here. Okay, so of course you want to determine the constants, right? Now, how to determine the constants, eh? Now, this equation is a function of x. So obviously you will need a condition on x to go and determine the constant, right? Make sense? You don't want to have condition on t because here no t, right? So definitely you want to make use of condition on x. All right. And what are the things condition on x, eh? Boundary condition. Yeah, boundary condition is condition on x, right? This is u0 t is 0, this one u3 t is 0, right? This one is when x is 0, this one is when x is 3. Okay, so it involves x. All right, so we want to use these two boundary conditions. Okay, and then can we use directly there? Then also cannot. Why cannot there? Because this one is u0t. This one is u3t. It's u there. But here it is fx. All right, so you cannot use directly. Okay, so what we do here is we need to like convert this. So how do we do the conversion? Well, actually we are using this uxt is fxgt, right? Okay. Yeah, so your uxt is fxgt. So let me type here uxt is fx gt. Okay, uxt is fxgt, right? That's what you assume, right? So therefore, u0t equal to 0. If you substitute inside x as 0, then straight away it will give you what? Straight away it will give you f0 gt is 0. Is it okay? All right, just by substituting x as 0 inside. And then from here, then we reason it out. Okay, you got f0 one item, then gt another item, right? So you two items, you multiply together, you get 0. So what does that mean? It means one of them must be 0. Make sense? You have one item times another item gives you 0, meaning that one of these is 0. Okay, so one of these is 0. So which one you want to choose as 0? Class f0 gt. Which one you want to pick it as 0?
f0.
You want your f0 to be 0. Okay, so from here you implies f0 is 0. Okay, now of course some of you will ask, why gt cannot be 0 then? Can you pick gt to be 0? Really cannot be 0. Cannot be 0. Okay, cannot be 0. GT cannot be 0. Okay, why GT cannot be 0 then? Because if your GT is 0, see what happened GT is 0. Suppose your GT is 0. Then what happens to your solution U? If your GT is 0, then straight away your U will become 0 Cannot be 0. Okay, so otherwise what Otherwise your U will become 0. Otherwise your uxt will become 0. Okay, and this is what then? This is called trivial solution. Right, so that's called trivial solution. Uxt equal to 0 means trivial solution. Right, trivial solution. And of course, you don't want trivial solution now. Because trivial solution is just 0 only, so it's not interesting one. Okay, it's a very obvious one. So it's not interesting, so you don't want this. Cannot. Yeah, so that is why your GT cannot be 0. And because GT cannot be 0, right? So the only choice is F0 is 0. Okay, so at least you come to here already. Okay, so similarly here also the same thing. Your U3T equal to 0, right? And you also put into your UXT. Yep, so this is what you have. You get F3 GT equal to 0. And then by the same reasoning here, your GT can't be 0. So that means your F3 is 0. Is it okay? All right, so now you see, you actually from your original boundary condition, originally it's like that, right? Now what you're getting is this one and this one. All right, and you can see that both of them involve your f. Yeah, involve your f. So now you can apply them. All right, so I'm going to apply f0 equal to 0 into 3. All right, so you just put your x as 0, okay? Then straight away you can get your a. Straight away you get your a lah. Okay, you found your constant a. Okay, substitute your a inside. Then you will just get this b term. You just get like that. Okay, now you use your f3 equal to 0. Put into your 4. Yeah, put into here. Put into your equation 4. So you substitute x as 3, right? So you get the b sine 3 lambda equal to 0. Okay, let me see. What did I put here? Yeah, so you will just get b sine 3 lambda equal to 0. Okay, then once again, there are 2 terms here. There are 2 terms. You see there are 2 terms here. One term is b, another term is sine 3 lambda. Then you multiply them and then you get 0, right? So same thing. One of them must be 0. Right? So which one you want it to be 0 then? You want b to be 0 or you want sine 3 lambda to be 0?
Sine 3 lambda.
Yeah, you want sine 3 lambda to be 0. Okay, let me explain. Okay, you tell me sine 3 lambda to be 0, right? So why b cannot be 0, right?
If b is 0, any value is also 0.
If your b is 0, then you put into your 4, that means your fx is 0 lah. Then fx 0, then your uxt equal to fx gt then also 0. Right? So the reason is otherwise, get what? Get trivial solution. Okay, so trivial solution. All right, and of course you don't want trivial solution. So that's why your sine 3 lambda must be 0. All right, and sine 3 lambda equal to 0 meaning what? 3 lambda equal to n pi. Yeah, 3 lambda is n pi, n is an integer. So that means lambda is n pi over 3. So your n is integers. All right, okay. So that's the best we can do. So we have found a. All right, we have found lambda. But the b here cannot be found. All right, because we have used up the 2 conditions already. No more condition. Okay, so that means b will still be b. So inside your equation 4, your b is still unknown, but you know your lambda already. Your lambda is n pi over 3. All right, so if we go and write this down, so this is your fx. Lambda is n pi over 3. Is it okay? All right, so you found your fx already. So now let's go and find gt. Okay, now go and find gt. So I must look at your I will need to look at the other equation, right? Involving gt. Where is the equation? That means this one. Equation 2. Okay, equation 2, you substitute your mu to be minus lambda square, right? Yeah, so that will give me this equation. Okay, and of course here, the lambda is no longer unknown. The lambda here is now n pi over 3. All right, still a constant, but we know what the constant is. Okay, go and solve this. It's a first order ODE. So, well, from your Maths A last semester, right? Go and solve all, you'll get like that. C is a constant. Okay, so now you've got your fx, you've got your gt. Let's put it together, then we'll get my uxt. So this is my uxt, so multiply, so this is what we have. So here b constant, here c also constant, right? So I just call it b prime. Okay, so this is a general solution. B prime is a constant and your lambda is n pi over 3. All right, why we call this general solution is because you still have unknown constant. Then your b unknown one. Right, so therefore we call this general solution. Everybody okay here? Okay, huh? Yeah.
Hello, bro. Can I check for the lambda, if we just put n pi over 3 instead of lambda, is it still okay?
You mean this lambda n pi over 3?
Yeah, in the general,
Oh, you mean the lambda here, you want to put n pi over 3, huh?
yes.
Yes, you can.
Okay, thank you, bro.
All right, so this one is a general solution. But we notice that this solution really, although you say you know lambda, right? But your lambda is n pi over 3 and your n can be any integer. Wow, so that is really, really very general. So what we do now is, because your n can be any integer, right? So we are going to do this thing called superposition. Yeah, superposition. So superposition meaning that if you go and sum all these, sum over n, sum over all the integers n, then that thing will still be general solution. All right. So this is what we are going to do next. So we say this is a superposition. Very super one. So the general solution there is like that. So we take the, let me change to like that. Okay, so that you can see. Okay, so now you can see both. So this thing here, I'm going to sum the n from minus infinity to infinity. And this will be the general solution. All right, so of course this one is even more general. So this is a general solution. This one is the general solution. Okay, you see, just put like that. And this b prime here, just now is a constant, right? I change the name, I change it to bn. Why I call bn then? Well, bn means, well, maybe for different n, this bn can be different number. So that makes it very, very general. Okay, so this one is the general solution. So this is the place, I think I put in the lambda, the n pi over 3. Okay, so now you see everything got n1, right? Bn, and here also got n, here also got n. Okay, so this is the general solution. All right, so of course there are unknowns inside. What are the unknowns inside? It's not the n, n is not unknown, because you'll see your n is the index. Your n is from minus infinity to infinity. All right, so they are integers. Okay, what is unknown here actually is the bn. Your bn is unknown. Yeah, your bn actually is unknown. Is it okay? So this bn unknown, right? So how to find this bn? You go and check your equation, your question here. The question actually on your right side here, right? So you realize that boundary conditions used already. Initial condition not yet used, right? So now is the time to use that. Okay, so now we are going to use initial condition. Okay, so initial condition is here. So I'm going to use initial condition. And initial condition actually means what? U x 0, right? So I'm going to substitute the t as 0 inside. Okay, now substitute t as 0. So can you imagine what we will get? U x 0. So bn is here, then you get e to the power 0, right? E to the power 0 is 1. And then you get this sine term. Is it okay? So this is u x 0. And what is it equal to? Well, actually, it's given in the question equal to these 3 terms here, right? These 3 terms here. So I'm going to put the 3 terms here. So equal to this. This one is given. Okay? Class, until here, okay or not? All right, So now this thing here, actually it will give us an equation. All right, so this thing here gives us an equation. This one equal to this. That's an equation, right? So from that equation, we are going to find bn. Yeah, we are going to find the constants bn. All right, so this equation, let me write it on the other side. Yep, let me write it on the next picture. So this one equal to this one. Is that okay? All right. So this is this. This one is the left side. This is the right side. Okay, so that's what we have. All right, so I'm going to, from this equation, I'm going to find bn. Right. So what can we say here? What can we say here? Okay, first thing, the left side here got how many terms? This left side here got how many terms, class? Summation n from minus infinity to infinity. How many terms here?
Infinite.
Yeah, infinite number of terms. But your right hand side only got how many terms?
3.
Right hand side only 3 terms. So that's one thing. That's one observation. And then the second observation is that, second observation very important. The terms on your left and the terms on your right, they are of the same form. Same form. Okay, what do I mean same form? Then you see the terms here. Bn sine something pi x. Correct? Bn is a constant and then sine something pi x. And then if you look at all the 3 terms here, they are also like that. Also constant sine something pi x. See here? Constant sine something pi x. Then this third term also like that, right? This observation is very important. They must be of the same form. Okay, it's because they are of the same form. So therefore you can compare apple with, compare apple with what? Class, fill in the blanks. Compare apple with?
Apple.
Apple. Okay, you can only compare apple with apple. You cannot compare apple with orange, right? So it's because they are of the same form. So you can compare them. All right, then you compare. So now your brain is working. Your brain is working. So your brain says, this one got infinite number of terms. Then here, that means infinite number of apples. Then here only 3 apples. Infinite number of apples. Then here only 3 apples. How is that possible? How is that possible? Why here infinite number of apples? Then here only left with 3. What happened? There's something to do with the constant Bn, right? What happened to the constant Bn? Why here infinite number then now becomes only 3?
The constant 0.
All of them 0, meh?
No, for those they are not n equals to after you compare.
Yeah. That's because a lot of these Bn's are 0. A lot of them are 0. Only 3 are not 0. Okay, so that is your conclusion. All right, so therefore we say, which are the 3 there? I also don't know. So I just call it the n1 term, the n2 term, the n3 term. Right, so that's why here you see that this is n equal to n1, this is n equal to n2, this is n equal to n3. Can you all see? So it is these 3 terms, non-zero Bn's, okay? And it is equal to these 3 terms here. Okay? Now even simpler. Now we just compare term by term. All right, so you can compare this term, you just match to this one. All right, so can you tell me what's your Bn1? Yeah, what's your Bn1? If you match this term to this term.
5.
Bn1 actually is 5. Okay, so you can see that Bn1 is 5. All right, and also if you match the something pi x, you can see that your n1 over 3 is actually the 4. Yeah, so that means you found the n1 also. Can you all see that? Is it intuitive? Very intuitive. All right, so you do the same thing here. This term, then you match to this term. Okay, and of course, this term, then you match to this term. All right, yep. So then you'll be able to get your Bn2. You'll be able to get your n2, and also your Bn3, and also your n3. Is it okay? All right, okay or not? Yep. And all other Bn's are 0. Any questions here, class? Okay, no questions. So have we found all the Bn's already? Hey, class, have we found all the Bn's?
Yes.
we actually found all the PNs already. All right, because you know that B12 is like that. This one is B24. This is B30. And all other BNs are 0. Okay, so you actually found all the BNs already. All right, so that means just now the general solution, all these BNs are now found. Okay, so let me go and write this down. Okay, so this one, let me go and write it down on the last page here. So UXT equal to this, right? So this is the general solution. And we have found all the BNs already. And we know that only BN1, BN2, BN3 are non-zero. All other BNs are 0. Okay, so therefore this infinite sum, you're only left with these 3 terms. Right, got your BN1, your BN2, and your BN3. This is n equal to n1, n equal to n2, n equal to n3. All right, so this is actually our solution already. All right, but of course, all these unknowns, now you already found, right? Put them in. BN1 put in, N1 put in, BN2, N2, BN3, N3, all go and put in. All right, okay, all go and put in, then that's what you have. Is it okay, class? All right. Any questions?
Hello, Prof.
Mm-hmm.
Just now you mentioned for the mu, right? In the lecture notes, explain to us why 0 and positive square cannot be used because it's trivial solution. So for this course, do we always use the mu as negative square?
Yes.
Okay, thank you, Prof.
Yeah, for this kind of equations. Yeah, for this kind of equations.
Okay, thank you, Prof.
Yeah. Okay, so we done number 2 already. Okay, so we'll stop here. Yeah, this is a long question. So class, we will stop here. All right, so we'll continue next week. Okay?
Prof.
Yeah.
I got one question.
Mm-hmm.
Can you go to the slide for question 2A, right? The one whereby you say the fx equals to a cosine lambda x. How do you actually get that?
You mean this one?
Yeah, the equation you underline.
Equation 3, huh?
Yes.
Okay. Okay, everyone can see this? Oh, this one is first order. Okay, so this one is a first order equation. Solving first order equation. All right. Just now you asked me that one is a second order equation. Wait, this one second order. Actually, just now we also have solving first order, right? So if this one is your equation, first order ordinary differential equation, then you in your maths A, you all got something called characteristic equation, right? So this one is the characteristic equation now. So it will give you this solution. And then, well, this will be the solution to the ODE lah. All right, so this is for first order ODE. Okay. Now for second order, say this is your second order ODE, right? You also have your characteristic equation. Your characteristic equation is like that. Okay. So if you go and solve this, you'll get this thing. So you will get your roots of the equation here, right? Now this one, there are two roots here. So there are three cases. Okay, the first case is these are two real roots, distinct, okay, distinct real roots. So you call lambda 1, lambda 2. Then in this case, then your solution to this, in fact, this is general solution. General solution to this second order ODE is like that. Okay, so this is first case. Then second case there is when your lambda 1, lambda 2 are identical roots. Okay, and they are real. All right, so in this case, this is the solution. And then we also have two complex conjugate roots. Okay, so that means your this equation, this solution turns out to be two complex roots. Okay, so in this case, your solution is like that. All right, in our case, where's our case? In our case, this one, you see the characteristic equation here is s squared plus lambda squared equal to 0. That's the characteristic equation. S squared plus lambda squared equal to 0. Okay, yeah. So if you go and solve this, your lambda, your s, sorry, not your, this one, you will get s equal to minus lambda square and then go and square root, right? So you will get your minus lambda square root there. So you are actually getting lambda I. Okay, so you are getting a plus minus lambda I. Lambda and then I. I is the complex root, the I, plus minus, of course. Okay, plus minus. I cannot put plus minus here. So it's a plus minus.
Okay, got it. Thank you, Prof.
Huh?
I got it. Thank you, Prof.
Oh, you got it already, huh? Yeah.
Yeah,
So
thank you.
plus minus I lambda. Yeah. So that means you get plus minus I lambda. You don't have an alpha here. Your alpha is 0. Okay, so that's why you get this kind. Is that all right?
Yes, thank you, Prof.
Okay. All right. So we complete this question already. So we'll carry on with this tutorial next week. Okay. All right. So if we have time next week, then we can do maybe 1 or 2 exam questions if we have time. All right. Okay then, class. Okay, good night.
Thank you, Prof. Good night.
Okay, bye-bye.